Yes, and today I have several things to discuss. The first, I think I made a wrong explanation on some parameters in support vector machine. It's related to quiz 9.1, so I would like to explain it again. And after that, we skip the support vector regression for now, and we discuss chapter 9 lab. And then we do exercise. So that is today's. So this is today's plan. So do you have any questions for other things? Except for quiz 9.1. Okay, so I review yeah. Slice. And slice itself. Slides themselves don't have any problems, but I made a wrong explanation on one slide. That is slide 15, I think. 15. Yeah. Yeah, so this part. So just to consider this equation and consider what is epsilon. And if the margin from the boundary is more than m, then basically observation satisfies the condition. So we have to set, we can just set epsilon I is equal to 0. And if the observation violates the margin of m in feature space, then we have some penalty, but the some penalty is allowed by this parameter c. And the last time, okay, so I explained this and this are m, that's correct. Then after that, I think I made a wrong explanation on how to determine epsilon. So suppose that okay, so think about this observation 11. Okay, so at first, this is the red area and area for red points, and this area is for blue points. So that means that this observation 11 violates the situation because this is not within this range. So how much it violates? So basically this amount. So if, yeah, so we have this is equal to 0.4 m. Then, yeah, this is 1 m. So actually, we violates 1.4 times m. So in such a case, epsilon 11 is equal to 1.4. And as observations, we can do in the same way. So for example, this blue observation, so it violates this amount. So if this is 0.3 m, then this is 0.7 m. So this is, okay, so epsilon 8, I think epsilon 8 is equal to 0.7. I think I may made a wrong explanation on this. So based on this, you can discuss, you can solve the question. Yeah, so basically the C is a kind of allowance for errors. So if you add up these all epsilon values, then you can get C. Yeah, so important thing is you have to standardize it by m. So if the distance between here and here is 1.4 m, the penalty is 1.4, not 1.4 m. And in the quiz 9.1, I think the m is 0.9, right? So yeah, so you have to standardize everything by 0.9, then you can solve it. And I think I wasn't sure if I made a correct explanation last time. So I extended the deadline for 1 day and I allow the up to 4 trials for that quiz. So if you haven't done correctly, you can do it by tomorrow at 11:59. Do you have any question? Yeah.
The value that you and I had discussed on the break or on the office hours,
Yeah,
was not the one that was in the solution. So
let me see.
I don't want to say class because it's still homework, but
Yeah.
the number you and I were had just done, and I said I was going to use, came back no. I do know what the answer was, and it was it was several decimal places off, or not in decimal places, several, at least several.
Okay, let me see. You may be right. Just a moment. So answer was set incorrectly, maybe.
That was my concern. If my number was right, if you and I were in agreement.
That's right. Yeah, actually, I got the wrong number. That's right. Yeah, I think that yeah, you are right. So maybe I have to correct it. Yes. Anyway, so you have the 2 more chances to answer. So
once you correct the final the correct value.
Yeah, I think that I just corrected the value now. So just a moment again. Yeah, I think. Yeah, I think it's corrected now. So yeah, you can take the quiz. So anyway, you have 2 more chances. So yeah.
Thank you.
Sorry about that. Yes.
I'll let you know if I get the same value. I'm just going to check it right now, since I have them memorized now. Be right back.
Yeah, so I remember that I corrected the answer a few years ago. So I think that when I import the homework from other years, probably I did something wrong, and that makes some error. Yeah, sorry for the confusion. But anyway, you have in total 4 attempts. You have 4 attempts. Okay. So now I want to discuss the chapter 9 lab. I think it's probably better to use the computer because this is R language. Okay, so let me see. Yeah, then after that, I want to do some exercise. So yeah. Yeah, so I want to briefly go over it, and there are many pages, but and I uploaded this slides just maybe 1 hour ago, 1 or 2 hours ago. And yes, so there are many slides, but many slides are similar, so probably it doesn't take much time. Okay, so support vector classifier. And we use library E1071. This is a pretty popular library in R. And just that for reproducibility, I set a seed for random numbers, and I generate the 30 random points on the XY plane, I would say X1, X2 plane. And just because of some reasons that I set the X1 as the vertical axis. Actually, the support vector machine package shows X1 vertically and X2 horizontally. So that's the reason. And okay, so 30 observations, and we put the label on these 30 observations. So first 15 observations, label is -1. And the next, the other 15, their label is 1. And if you randomly just generated these 30 points, then of course we cannot distinguish it. Yeah, so in such a case, we cannot really distinguish it. So I shift the observations with label 1. So we shift the observations to the right and to go up. So to go up by 1 and to go right by 1. So these the red triangles are basically on average have so these red triangles, the x1 values and x2 values are both larger by 1 compared to the black crosses. So just I artificially add the 1, 1 vector for each point. So that's why the triangular points are red triangles are on the upper right side, and these black crosses are just centered at 0. Yeah. So then this is just sample data. So I would like to make a straight line to separate these two sets. So since I added 1, 1 vector, probably the straight line is around here, and probably slope with -1. So that is a reasonable expectation. But it's not perfectly separable because anyway, if we use straight line, so these two will be errors, and also probably this cannot be classified correctly. So at least maybe 3 or 4 errors. Yeah, so I just differentiate these points by color and point character. Y is equal to 1 if red triangle, y is equal to -1 for the black crosses. And and I set the data frame D, and we use the SVM function. SVM function is used for both classification and regression. And the format is similar to usual regression. So Y on, this is all the other variables in the data set, Y tilde dot. And we can specify kernel. So linear kernel is basically a kernel with linear boundary. So this is just the same as, basically the same as the linear discriminant analysis. So we have some, the penalty. So we have some difference, but basically linear classifier. So similar to LDA. Okay, and this is the cost. So cost is hyperparameter. So we have the hyperparameter C, right? You can see the hyperparameter C. And the cost is a kind of the inverse proportional to C. So maybe not exactly inverse, but as cost increases, then C decreases. So hyperparameter, which is a function of C, and decreasing function of C. And I didn't specify many options, but we can specify several things. At first, the kernel we have specified, but we have other options, at least the polynomial, radial basis, and sigmoid. So these are other candidates. And the polynomial kernel and radial basis we have covered in lecture. Sigmoid is a kind of the logistic curve. So basically, this maps the entire real numbers to 0, 1. So you can see the explanation in the help of SVM function. So this is the help page of SVM function. So you can find this in E1071 package. So we have many options. Some of them are just the same parameter in different expression, but we have several ones. And yeah, we can also we have also the explanation on kernel. So what's the kernel? What's the inner product in the feature space? The linear kernel is usual inner product. So basically, we use identity map for feature map. Yeah. And the polynomial kernel that we have discussed it. And basically, we have the two functions, gamma and the coef 0. I think the maybe just one parameter. You can either change gamma or the coef 0. So if we change both, then basically we have the same function. Right? If we make gamma twice as large and coef 0 as twice as large, then the result is basically the same. You know, everything is expanded, but the geometry is the same. Similar, I mean. And the degree is either so usually we use 2 or 3. Maybe we can have a higher degree. So the higher degree, we have more complicated inner product, more complicated feature space. And the radial basis function, I think some typo here, but the e to the power negative gamma times the absolute value of u minus b square. So gamma is a hyperparameter. And the sigmoid function, again, either gamma or coef 0 is our hyperparameter. And this is, so hypertangent. So so basically this is kind of similar to the logistic curve. And you can see some the default value. So it's interesting that the degree is equal to 3 is default for polynomial kernel. And the gamma, I don't know about this justification, but the gamma is set to be 1 over the number of variables, number of predictors. So you can change it, but this is default value. And coef 0 default is 0. And cost function default is 1. Yeah. And new is another form of the penalty on support vector machine. So I think that this is a function of cost, but it has different representation. So you specify either cost or new. You can search on the internet about what's the parameterization of mu. Yeah, and some other more minor variables. Yeah, maybe some are only for regression, but so this is SVM. So you can use SVM, and here we use linear kernel. And the linear kernel, anyway, boundary is linear. So cost function does not matter much. Depending on cost, the C is determined, and the M margin is determined. But regardless of margin, anyway, the boundary is linear. So it doesn't make much difference. The scale is whether or not we scale x1 and x2. If true, then this is standardized. So mean becomes 0 and the variance becomes 1. That makes more sense because we make the margin largest. So if all variables are standardized, probably it makes more sense. Yeah, I think that if scale is false, then result depends on the unit of the predictors. So that is not preferable in most cases. But in this case, we know that x1 and x2 are both random numbers with the same variance. So probably scale false is appropriate. Then we plot. So this is the so the plot of support vector machine. So so these points are the same as the previous, the scatter plot, and the color represents the same thing. Red is the one, and the yellow is red. red points are y is equal to 1, and the black points are y is equal to -1. And support vector classify the entire space into this red area and the yellow area. So this is the y is equal to 1 area, and this is y is equal to -1 area. And these crosses are support vectors. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14. I think 15 I wrote. I saw the 14, 8, 10, yeah, 15. 15 support vectors here. So I'm not exactly sure about the place of dotted line. So the black area here, support vectors, black area here. So these are, the classified correctly, but still support vectors. So I think the dotted line is around here, and probably this side it's not clear. Maybe around here, yeah. So this is the area. So even if the black points are in yellow area, still it's within margin, then it's support vectors. So these are support vectors. So these black crosses in yellow areas are classified correctly, but within the margin of M. So these are support vectors. If black point go to the other side, of course, this is a support vector. It violates the rule. And red points, even if these are correctly specified, still it's within the margin of M. So these red crosses in red area are support vectors. And of course, if red points are on the other side, these are also support vectors. Do you have any questions? I think there is no meaning about this zigzag line. So this should be linear, but just the algorithm makes it not smooth. I mean, the graphical algorithm, yeah.
I'm not sure how much resolution it actually did, because that just looks like aliased. That looks like aliasing.
Yeah. You can have a higher resolution with the more computational power, I think. And okay, so this is based on the, I think, default, no, the cost is equal to 10. Cost is equal to 10. And if cost is different, then slightly different. So cost is 0.01. Smaller cost. So that means larger C, more allowance. So that means that we have larger margin. So if we draw dotted line, probably dotted line is around here and around here. So basically all points are crosses. So basically all points violates the M margin rule. So M is so large that all observations violates the rule. So because the C is very large, that means cost is very small. But anyway, so the this boundary doesn't change much, maybe slightly different. Maybe slope looks slightly smaller, closer to 0. But anyway, so this. And first one, actually, we see the support vectors. You can see the SVM fit. This is our SVM result. Then $ index. Then we see the indices for support vectors, and we have 15 vectors. But here that we have all, I think, 30 vectors. So all 30 observations are support vectors. Okay, so now that we want to optimize this cost parameter. So usually this support vector machine, neural network, almost everything is automatic, but except for hyperparameter choice. So hyperparameter should be chosen by some cross-validation. And this tune function, I think this is also in E1071 package. So this basically make a grid search. grid search for parameter within this range. So here I optimize the parameter, the cost. So we try cost is equal to 0.001, 0.01 and 0.11 and 5. 5 is strange, but the 10 and the 100. Then yeah, I put 5 because 5 is the best one. And yeah, then you can get this. So basically this did cross validation to calculate error size. And you can see that the this cost is equal to 5 is the optimal one with smallest error, so 0.2. And actually 0.2 is also achieved by the parameter of 10. Cost is equal to 10. Why this is not chosen? I think that cost is large, then C is small. And if C is small, separation rule is slightly more complicated, I think. So if the performance is the same, they use the simple one. So that's why probably they choose 5. Cost is equal to 5. Then, so okay, so now we know that cost is equal to 5. So you can investigate what's happening, and support vectors. Number of support vectors is 15. So I think this is the same as the previous result. And this is the prediction performance. All right. Okay, so we want to make the training error and test error. So actually, sorry, this only tried test error. With cost 0.01, we can make a prediction with the best support vector machine model with the new data set. This is the test data set. Then we make a table of predicted value and true value. So the test set is made by the same algorithm as training set, but more observations. So we generated 100 observations with the same algorithm. Sorry? Yeah. Then actually the 78 observations out of 100 observations are categorized correctly. Cost is equal to 5. Actually, this is almost the same support vector machine. And actually we got the same answer. Yeah, so if we have larger training set, then maybe these costs they should have different test error. But this one, just by chance, that these two don't have any difference. Yeah, this is just another example with separable case. So last example, we have some overlap between these black crosses and red triangles. So I add another vector to move these red triangles to the upper right. So now it's linearly separable. Then we fit the support vector machine. And I set just a large cost because we know that this is linearly separable. We don't need C. So large cost corresponds to small c. So extremely large cost. That should be fine. Oh, yeah, and the cost, to be exact, what this cost means. Okay, so this is basically inverse proportional to C, but the exact definition is here. So if we give some cost is equal to 10, then support vector machine, the minimize this quantity. So this is basically the sum of squared coefficient in support vectors. Yeah, so sum of the squared coefficients on the support vectors, the regression model, and plus the cost times summation of epsilon I. So if the some observations violates the M margin rule, then we have the large penalty on it. So basically, it cannot violate the rule, the M margin rule. Okay, then what happens? Then actually we see that we only have two support vectors, and the result is here. So obviously, this observation and these observations are closest to boundary. So just we connect these 2 points, and just the line which is perpendicular to the this line segment, and also it just goes through the midpoint of these points, 2 points. So that is the separating the hyperplane. Yeah, last time that I said that if 2 predictors, the 3 support vectors are most typical, but I think that maybe for separable case, I think the 2 support vectors are maybe more common. Yeah. Of course, 3 is possible, 4 is also possible, but I think the 2 may be more typical in this case. Yeah, for separable case. Yeah, I think this doesn't make much sense. So just I use the linear kernel with the cost is equal to 1. And yes, we have larger margin. So still we have the 5 support vectors. Yeah. But anyway, so this is linearly separable. So probably a large cost is good. Okay, so do you have any questions so far? So if not, we go to the next section, the support vector machines. So there are 6.1 is just a linear classifier, but now that we have more interesting the one. Maybe seeing this is maybe easier to understand. So I generate random numbers, pair of random numbers from negative 1.5 to 1.5, or maybe I just use yes. So just uniform random variable from negative 1.5 to 1.5. Then I classify these observations as within unit circle and the outside of the unit circle. So that is what I did here. So I generate 200 points using the uniform random numbers. And we define y as this condition. So if the point is within the circle, then y is true, and the outside, y is false. Make the circle. Then other lines are just to make this plot. So now that we want to do the support vector regression. So you can see that the linear boundary makes poor sense. Maybe it's possible if we make a line which touches this unit circle. Maybe one side is all the black circles and the other side is the mixture of red and blue. The ratio of number of red points and the black points, the just ratio of the area. So this is 3 by 3, so 9. And the within circle, that is 1 times 1 times pi, so pi. So pi to 9. Actually, if you generate random numbers and make a circle, then you can actually calculate the, you can actually calculate the what's the area of the circle is. So by random numbers, you can approximate area of a circle. Anyway, so this ratio is pi to 9. So pi to 9 is a difficult situation here. For example, if we make, for example, this line as a separating hyperplane, then this upper left area is very small, all black, but it's very small. But the other side is majority of the area, maybe area is the 7 or 8. Then still inside the circle is not less than 50% of the area. So that means that if we have this separating hyperplane, this side is black, this side is mixture, but in a mixture of black and red, still black is dominant. So actually we cannot really classify by straight line. So maybe the best line is here, but still the both sides are black. The majority is black. So we can imagine that linear classifier performs poorly. And I try several ones. First one is the linear kernel. And the second one is the polynomial kernel with degree 2. Actually, boundary is degree 2. So actually, this is the correct model, a kind of correct model. Of course, we have some redundant terms like xy, x times y. But this is correct model, basically. And the polynomial kernel with degree 3. So this includes all the quadratic terms. So it can classify observations, but we have redundant terms such as x cubed, y cubed. So probably it's slightly less efficient than P2. And radial basis kernel. So this is basically the one-size-fits-all solution for support vector machine. So infinite dimensional space. But when we know d is equal to 2 is sufficient, the radial kernel is maybe too much. So maybe it's better than linear kernel, but probably the worse than polynomial kernel for this case. So this is linear kernel result. So yeah, actually support vector is 83. So there are so many. In total, we have 200 observations. I think 200, yes. And the second one, actually, polynomial with degree 2, only 4 support vectors, a very simple rule. Polynomial with d is equal to 3. And we have 85 vectors, so it's not so many. Radial basis kernel. Actually, that works somewhat well. The support vector is 34. So rule is not super complicated. And the linear kernel here. So basically, for any straight line, in both sides, black points are majority. So actually, all points are classified as false. Black. False is black, true is red. So this is linear one. And this is the support vector machine with the polynomial kernel with d is equal to 2. So within circle, so this is classified as the true, and outside classified as false. So only a few exceptions. So maybe this one is categorized incorrectly, possibly this one, maybe only 2. So very accurate. And d is equal to 3. It's a kind of similar to d is equal to 2, but it fails to classify the 2 groups. So it's a kind of surprising. D is equal to 3 includes D is equal to 2, but it does not work. So it's really hard to imagine what's happening in feature space. And this is radial basis kernel. So this works pretty good. So it's similar to D is equal to 2. Training error. So linear kernel always predict as false. It does not make any sense. And the polynomial kernel with D is equal to 2. The training, actually everything correctly. And the test set, there are only 2 observations classified incorrectly. So basically they miss to calculate the correct radius and the correct location of the, and also the correct angle of the ellipse. And P is equal to 3, actually it performs poorly. And radial basis, actually it works well, but the out of sample performance slightly worse than these polynomial with D is equal to 2. Yeah, so that is the classification part of support vector machine. And yeah, now I would like to do the exercise. Maybe I can share the screen first. Exercise is also available on the website. So just I want to see this. Yeah, so orange juice data set. This is the marketing data. So 2 brands of orange juice, and which one sells more, we want to predict. So I think there are about 15 variables, maybe 18 variables in this data set. And it contains 1070 observations. So each observation is a purchase. And whether they purchase the Citrus Hill or Minute Maid orange juice. So first, separate the training set and test set. So actually, this is random. So based on this, your performance is different. Then support vector classifier with the linear kernel with the specific cost function. Then yes, get the output and calculate training and test errors. And what happens if the cost will change. And also what happens if kernel is radial or polynomial with D is equal to 2 or a sigmoid kernel and so on. One thing I have to note is that we can optimize the multiple parameters using the tune function. So maybe I just go back a little bit, sorry. Yeah, so you can see that the in tunes function, you can see that the list of something. So list of the cost is equal to something. So if we want to include more parameters, you can just put comma and, for example, coefficient 0, coef 0, coef 0 is equal to a list of numbers. Then they do grid search. If we have the 5 different costs and 3 different coef 0, then we have 15 simulation here. Okay, so now we start. Do you have any questions? Otherwise, I split the room into how many? Maybe 2 breakout rooms. So, James, Victoria, who is here? So, Nathan. Maybe I move to Nathan, 1, and maybe James to root. Yeah. Okay, so maybe about 20 minutes. 20 minutes.
telling people all sorts of things. I can't, and I was doing it in mute.
Okay, so yeah, so we continue next time. So in machine learning models, we don't have model selection, but we have to tune the hyperparameters. And at least I would like you to struggle with it for 1 hour. So we continue next time. Yeah. And if you don't have any questions, see you on Wednesday.